Welcome, everyone. Today, we'll dive into some exciting competition problems using Möbius inversion and explore helpful strategies along the way. We just finished building a full Möbius toolkit in the first 11 lectures, so now we get to see how it actually wins contest problems.
So today is less about new theorems and more about how to recognize when to use them during a timed competition, right?
Earlier lectures gave us definitions of mu, the inversion formula, and how Dirichlet convolution behaves like algebra on arithmetic functions.
So we will focus on just a few problems, but go deep into the moves and tricks behind each one.
Exactly. The real skill is spotting a familiar pattern quickly, so you know when a Möbius detector or a convolution identity is the right tool. For each problem, we will identify the key insight, walk through a clean solution, check it on an example, and then extract a reusable contest takeaway.
I like that it is basically a clinic. Do, diagnose, and then generalize a pattern I can recognize next time.
Exactly. And the next slide is all about those patterns that shout, use Möbius here. Before diving into the problems, let us name the signals that tell you a Möbius trick might be hiding in a statement.
That would help a lot, because in real contests I do not have time to try every technique blindly.
If you see a coprime condition, that is the classic place to insert a Möbius detector over the greatest common divisor and then reverse the order of summation.
So if I see something like a function defined by adding values of another function over all divisors, I should suspect an invertible convolution is behind it.
Right. A sum over divisors of n with a product depending on d and n over d usually screams Dirichlet convolution, which lets us use simple algebraic rules. Whenever the problem talks about primitive objects or minimal period, there's often a hidden sum over all divisors of a period, and Möbius inversion lets you isolate the primitive part.
Got it. So I should be on high alert for coprime conditions, divisor sums, and primitive language.
Exactly. And our first problem will be a quick convolution warm-up to get those reflexes going. Let us start with a Putnam-style warm-up that is pure convolution algebra.
This is where recognizing the convolution structure should really pay off.
Here, S of n is defined as a divisor sum, where each term multiplies mu of d and sigma of n over d. Sigma of n is the classic sum of divisors function, adding all positive divisors of n.
So the question is whether this complicated-looking divisor sum actually collapses to something much simpler in n.
Right away, we should see that S is literally the Dirichlet convolution of mu and sigma. Instead of grinding the sum directly, we will use algebraic rules for convolution, like associativity and known identities.
So the strategy is to factor sigma into pieces whose convolutions with mu we already know.
On the next slide, we will factor sigma in the cleanest possible way and then let the algebra do the work. The key identity is that sigma itself is already a convolution of two very simple functions.
If we can rewrite sigma that way, then mu star sigma should break apart nicely.
We can write sigma of n as the convolution of the identity function, which sends n to n with the constant function 1. Using associativity of convolution, we can regroup the product mu star sigma as mu star identity, all of that star 1.
So the constant function 1 just ignores n and always returns 1.
Right, the identity function here is just the function that outputs its input n. The big win is that Dirichlet convolution is associative, so the grouping of factors does not matter.
So it all boils down to recognizing what mu star identity equals.
On the next slide, we recall that mu star identity is just Euler phi, which makes the whole expression collapse. Now we plug in a standard identity and watch the convolution telescope down to something extremely simple.
This is where memorizing a few core convolutions really pays off.
First, we recall that mu convolved with the identity function gives Euler phi, the totient function. Second, phi convolved with the constant 1 function gives the identity function that outputs n. Putting the pieces together, mu star sigma equals phi star 1, which equals the identity, so S of n is just n.
For n equals 6, the terms are 1 times 12, minus 1 times 4, minus 1 times 3, plus 1 times 1, which really does give 6.
The first key memory item is that mu star identity equals Euler phi. Because sigma is identity star 1, regrouping gives mu star sigma as phi star 1.
And we know that phi and the constant 1 function convolve to the identity that returns n.
So all the structure in the sum collapses, and the final answer is simply S of n equals n. Always good contest practice is to test a small value like 6 to confirm that your algebraic simplification matches the original sum.
So if I see mu times a familiar arithmetic function in a sum, I should immediately ask whether regrouping makes it a composition of known convolutions.
Exactly. And the next problem shifts from pure algebra to a counting question about lattice points and fixed greatest common divisor. Now we move to a geometry-flavored counting problem on the integer lattice.
This sounds like one of those grid problems where greatest common divisor secretly controls visibility.
The problem asks for the number of integer pairs in a 100 by 100 grid whose greatest common divisor is exactly some fixed value d.
Usually I have seen the case where greatest common divisor equals 1, so here we are generalizing that question.
For a concrete check later, we can keep in mind the special case where the greatest common divisor is 6. The natural idea is to pull out the common factor d from x and y, and then count coprime pairs in the smaller grid.
So if I can translate fixed greatest common divisor into a coprime condition on scaled variables, I can reuse the Möbius detector.
Let us formalize the idea of factoring out the common divisor d from both coordinates.
This is that standard trick. Write x and y as d times something and encode the greatest common divisor inside that something.
Having greatest common divisor equal d is equivalent to x and y both being multiples of d, with the remaining factors a and b coprime. Because x and y are between 1 and 100, the new variables a and b must lie between 1 and the floor of 100 divided by d.
So the number we want, really, is just the number of coprime pairs a and b inside that smaller square grid of side-length floor of 100 divided by d.
The change of variables from x and y to a and b makes the fixed greatest common divisor condition completely explicit. Now a and b themselves are forced to be coprime, which is perfect for using a Möbius detector.
The scaling also shrinks the square from side length 100 down to side length floor of 100 divided by d.
That means our fixed greatest common divisor problem is nothing more than a coprime counting problem on a rescaled grid. Now we can plug in the standard Möbius formula for coprime pairs up to n and tailor it to our count d. Let us write down the general Möbius formula for coprime pairs and then specialize it to our situation.
This is the one where we insert the detector on the greatest common divisor and then change the order of summation, right?
In general, the number of coprime pairs up to n equals the sum over k of mu of k times the square of the floor of n divided by k. For our problem, we replace n by floor of 100 divided by d, which produces this formula for count d.
For d equals 6, we get terms like 1 times 16 squared, minus 1 times 8 squared, minus 1 times 5 squared, minus 1 times 3 squared, plus 1 times 2 squared, and so on for each square-free k up to 16.
The formula comes from writing 1 if a and b are coprime as a sum involving mu over divisors of their greatest common divisor. Then we swap the order of summation and just count how many a and b are multiples of a given k using floor functions.
Specializing n to the side length of our scaled grid then gives the desired count d formula.
In computations, it helps to remember that only square-free k matter, because mu of k is 0 when k has a squared prime factor. The contest level insight is that fixed greatest common divisor questions can often be scaled down to the standard coprime case.
So when I see greatest common divisor equals d, I should first factor out d, and then immediately think of the coprime pair formula.
Exactly. And now for the third problem, we will move to primitive roots and group orders, another classic Möbius playground. Our final problem lives in modular arithmetic and group theory.
I know primitive roots are generators of the multiplicative group modulo a prime, but I have never counted them with Möbius before.
For any prime p, the non-zero residues modulo p form a cyclic group under multiplication, and the size of that group is p minus 1. The question is simply, how many generators does this cyclic group of size p minus 1 have?
Right. A primitive root modulo p is just an element whose order in the group is p minus 1.
Since the multiplicative group is cyclic, every element has some order that divides p minus 1. So we can forget about modular arithmetic for a moment and just ask, in a cyclic group of given size, how many elements have each possible order?
Once we know how many elements have order d for each divisor d of p minus 1, the primitive roots will just be the case d equals p minus 1.
Let us analyze the distribution of element orders in any cyclic group of size n.
Once we can count elements of each possible order, we can just plug in d equal p minus 1 for primitive roots.
If n of d is the number of elements of order exactly d, then summing n of d over all divisors d of n must give the total group size n. More precisely, for each divisor d of n, the elements whose order divides d form a unique subgroup of size d, so the sum of n of e over all e dividing d equals d.
This is exactly the kind of divisor sum where we can apply Möbius inversion to solve for n of d in terms of d itself.
Carrying out the inversion shows that n of d equals Euler phi of d. So there are phi of d elements of order exactly d in a cyclic group of size n. We start by defining n of d to be the number of elements of order exactly d.
Because the group is cyclic, there is exactly one subgroup of each size dividing n. So the elements whose order divides d form the subgroup of size d.
That subgroup perspective gives the relation where sums of n of e over divisors amount to the size d. Applying Möbius inversion to that divisor sum immediately yields n of d equal to phi of d.
So as soon as I see a cyclic group, I can automatically say there are phi of d elements of each order d dividing n.
Now we just plug d equal p minus 1 into our formula for n of d to count primitive roots.
It is nice that the answer ends up being a single evaluation of Euler phi.
Since primitive roots are exactly the elements of order p minus 1, the number of them is phi of p minus 1. For example, when p equals 13, p minus 1 is 12, and phi of 12 turns out to be 4.
Similarly, if p equals 17, then p minus 1 is 16, and phi of 16 is 8.
By definition, any primitive root has full order p minus 1 in the multiplicative group. Our previous result says that, in a cyclic group, the number of elements with a given order d is phi of d.
Putting these together, we get that the number of primitive roots modulo p is just phi of p minus 1.
In contests, this means your main job is to factor p minus 1 and then evaluate phi from its prime factorization.
So, as a rule of thumb, whenever I see primitive roots mod p, I should immediately think phi of p minus 1.
Let us gather the patterns we have seen into a quick contest playbook.
This is what I want to remember in the middle of an exam. Not every derivation line by line.
Whenever you see a coprime condition, try writing 1 or 0 as a sum over divisors with mu, and then swap the order to count multiples cleanly. If the statement defines a function by adding values of another function over divisors, treat it as a convolution and use inversion to solve backward.
So messy divisor sums often simplify a lot once I rewrite them as convolution of standard functions like mu, 1, identity, or phi.
Primitive roots, primitive necklaces, and minimal periods all tend to come from a total count expressed as a sum over divisors, which Möbius inversion can reverse.
So GCD, divisor sums, and primitive language are my big 3 warning lights that tell me to try a Möbius-based attack.
Exactly. And we will finish with a short exit problem plus a reflection to lock in these habits. Let us close with a quick symbolic practice problem and a reflection about strategy.
I will try the algebra on my own first, then check with your explanation.
Recall that tau, the divisor counting function, is just the convolution of the constant 1 function with itself. Using mu star 1 equals the identity for convolution, you can see that mu star tau equals the constant 1 function, so the value is 1 for every n. Start by writing tau as 1 convolved with 1, then regroup mu star tau as mu star 1, all of that star 1.
So mu star tau is mu star 1, which is the identity function star 1, giving just the constant 1 function, meaning the answer is 1 for every n.
Take a moment to decide which pattern you want to watch for most actively, whether it is coprime conditions, divisor sum definitions, or primitive language.
I think I will train myself to notice coprime or fixed greatest common divisor conditions first, since those seem to show up all the time.
Great. Keep drilling these patterns on old contest problems, and Möbius inversion will start to feel like a natural reflex. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback. Leave questions and suggestions in the comments.